Alright, today we're going to talk about sound intensity, but first I want to start with a short visualization here. Imagine the sound is being produced at a source, and that sound energy is being carried out from a central point along the surface of a sphere, and that would look something like this. As I'm drawing pictures in a moment, I'll be drawing circles, but I want you to realize that these are actually just cross sections of a sphere of sound going outward. Right, so sound intensity. If you have some kind of sound event and that energy starts to spread out, you might start off at a certain radius, and then sometime later, sound energy has gone further, and so you end up with a greater radius, right? So let's look at the equation for sound intensity. This is power over area. Power is the rate that energy is leaving a source. So if you want to increase the intensity of your sound, one way is to increase the rate that energy is leaving. But oftentimes this area comes up because as you get further away from a source, the area that energy is spread over increases. And let's look at by how much. The surface area of a sphere is given by (4 pi r squared). Okay, so when we divide, we get intensity equals power over 4 pi r squared. And I want you to pay especially close attention to this r squared term, because that gives rise to something called the inverse square law. And in physical situations where you get this 1 over r squared term, we call this inverse squared because we have an r squared in the denominator. And let's look at what happens as you get further and further out. If you get 2 times farther from a source, we get 1 over 2 squared, which is 1/4 the sound intensity. So the sound intensity would actually be just a quarter of what it was if you were standing half as close. If you move 3 times further away, you get 1 over 3 squared, which is 1/9. So the sound intensity goes down by a factor of 1/9. If you're 4 times further away, you get 4 squared, which is 1 over 16, so you're a 16th as much sound intensity. 5 gives you 1 over 25, 6 gives you 1 over 36, and so on and so forth. So as you move away from a source, you decrease according to the inverse square law. Now, there's something else that's also going on with sound intensity. So let's get back to thinking about intensity in terms of power. Okay. If you increase the power output or change your position so that the sound intensity is increased by 10 times, we would set this equal to, or at least it's equivalent to, plus 10 decibels. So every time you have 10 times the intensity, you get plus 10 decibels, right? And if we add 100 times the intensity, gives us plus 20 decibels. Where did that 2 come from? Well, 100 equals 10 to the 2, and we take that 2 and we put it right there. 1,000 times the intensity gives us plus 30 decibels, because there's 3 zeros right here. 1 0 is plus 10, 2 zeros is plus 20, 3 zeros plus 30, 4 zeros plus 40, so on. And that shows you the logarithmic relationship between sound intensity and decibels. Lastly, let's think about loudness. When the decibel level goes up by 10, just plus 10 decibels, you might be tempted to think that it would sound 10 times as loud. But in fact, the loudness will actually be 2 times as loud. So you would perceive the sound to be twice as loud as it actually is. Plus 20 decibels is actually times 2 to the second power of loudness, which is also known as times 4 loudness. Plus 30 decibels is times 2 to the third loudness, which is the same thing as times 8. So when you add 30 decibels, it's not 30 times louder, it's not 10 to the third times louder, it's 2 to the third. So loudness and sound intensity scale with each other, but they scale by different with a different base. So intensity scales up by factors of 10, loudness scales up by factors of 2. All right, that's it for today.